start the very last lecture of the day and also the last talk before we start the field trip part of the summer school. We're very happy to have Professor Rehfeld with us. She is a professor at the Institute of Environmental Physics at the University of Heidelberg. And her research is broadly concerned with the understanding of the dynamics underlying Earth's climate variability through space and time using proxy networks and numerical models. And today she'll teach us all about the SISAL data.
Thanks very much for the introduction, and thanks very much for the invitation and trusting me with the last presentation on the last day of the workshop before we all go out and do what we love, which is going outside. My name is Rehfeld, and I'm at Tübingen University now. It's not fairly recent. And I will, indeed, tell you about how we can do science with synthesis. So going from a multi-proxy perspective to a perspective that allows us to scale to larger, maybe regional scales, but also even global scales. So towards the scale of a grid box of a climate model. And I will convince you that this is a great idea and show you ways on how you can get started right away. I am acknowledging here in particular my co-authors from the SISAL database, Nikita, Franzi, but also Janika. She's a former PhD student. I don't think this is working.
No, it's just a pointer.
Okay, so yes, Janika is a former PhD student, and Alaya, I don't know how many of you know Alaya, but Alaya was instrumental in building the first version of the SISAL database. And I spent a lot of time with H models with her. I'll tell you a little bit of that later in the talk. Then I acknowledge the Spacey Research Group. Baldur is a part of that in Tübingen, and all the SISAL working group members. But before we go into SISAL, and I should do this, briefly, who of you has been to Tübingen? And knows, well, 1, 2, yes! 3 people. This is, if you look at southern Germany, roughly in the center there, we have the Alps, and here we have Tübingen. It's quite hard to get to, but if you do, this is what you find. At least this is a picture I took from Tübingen City Hall website. It's quite nice. We have a fancy or not fancy, but we have a castle. The geoarchaeologists work there. However, that's our daily environment. This is the campus, the science campus at the top of the hill. You can imagine the castle is down there. And this is the brand new Geo and Environmental Science Research Center, which includes a paleomag lab. And we work here on the 5th floor. The other floors are underground. So Tübingen, or the sciences in Tübingen, have really also revolved around paleo work, so describing the environments, because what you see in the distance here are basically Jurassic sediments, when all of this was at the bottom of the sea, and it preserved a lot of the life that was in the sea. And there were very early on professors and researchers studying those deposits. Later, what we do most of the time when we go to the city center down there, which is where, I don't know if I can go back, which is where this collection is still on display. So this is about 300 meters up from this bridge, is where the old institute building was. So when we go down there, we go there to have fun, and boating on the river is a tradition that Tübingen shares with Cambridge University, for example, or Cambridge in the UK, for example. We also have something that I only learned about very recently, actually to be fair, last week when I made the slide, that we had the first female student in Germany, in Tübingen, and she was a student of one of the geoscience professors, or at that time it was called slightly differently, not geoscience. So this is Maria von Linden. She was the first one to get a high school diploma in the state and also in the wider area. She was the first one to go on to get registered as a student, but by then it was only case-by-case basis. So this was in 1892. She was registered for studying after the king intervened on her behalf. She also then was the first one to get a doctorate, the first one to head zoology lab, and the first one to become a professor in Germany, the first woman. So it's pretty impressive. All right, but we actually want to talk about SISAL and SpeedFM databases, not about you, which is great. So hands up if you have heard of SISAL before reading about this. Yay! Okay. So there were some hands that didn't go up, so I'm glad. There's something in this for you. I read a paper in depth, not just read the title, where SISAL data was used. All right, cool. Quite a few hands going up. I've used SISAL data myself. So few in the back. Okay. I've contributed to the SISAL database. I see some cool fewer hands. So that could be in terms of working in SISAL. This could be by contributing data, quality control, analysis. So this can be in many different ways and is recognized. Or I've contributed to SISAL research. So I've written one of those papers. Anyone? Yeah, cool. Okay, so I think there will be in it something for all of you. I will do my best, and so now here's my outline. So I'll talk a little bit about what is SISAL, since many of you have already some ideas. Maybe not so many things that are new, then a bit about SISAL science and where SISAL is heading. So why does SISAL matter, and what is SISAL in the first place? What's the acronym standing for? Anyone? I hear some in the room. Anyone? Don't want to put you on the spot. SpeedFM, isotopes, synthesis, and analysis. Yeah, I saw you got it right. So at the bottom of the heart stood the question, how to interpret isotope signals in SpeedFMs. And that was in the first phase, predominantly oxygen and carbon. It's already a start of a multi-proxy experience in a way, because a lot of times in the past, what happened when you were looking at data, you had one part that made sense and the other part of your data that didn't make sense. And so a lot of C13 data, for example, was always buried somewhere. It wasn't available. So putting this together at a scale so that it can be regionally and globally interpreted was the first goal. So SISAL is a PAGES working group. PAGES is the Past Global Changes Network, and I'm not going to repeat the hands up. It's a great network. Phase 1, 2017 to 2019, built this first global database of SpeedFM isotope records. I think in the first one we had something like 348 records, focusing on oxygen and carbon. That was published in 2018. Version 2, that's the one where I was heavily involved, had then more than 700 records, and this was the heavy lifting that Laia and I did on the train back from the workshop, the SISAL workshop in China, back to, well, Moscow in that case. We looked at the standardized age models, so we reconstructed age models for 500 of the 700 records. Quite a few of them didn't have any, or there were no uncertainties, or they were calculated in many different ways. And I can tell you I've seen a lot of age models, and yes, that was version 2. So now that's the one that you can download, and I will show you where to download right away. In phase 2, we've been giving attention to cave monitoring, having a conversation towards process modeling, and including trace elements. Who of you has contributed trace element data to SISAL? Okay, I know. Okay, I know at least 2 people here in the room have. And so that is now going into the third version of the database, which includes now 902 records. It does include trace elements for, I think, more than 70 scans of the records and cave maps that are all linked to the entities, so all available to you on a click. So yes, if you want to see more about that, go to pastglobalchanges.org and find the SISAL page. There is a conversation right now going on about where SISAL is heading in phase 3 and who will pick up this conversation in phase 3. So, first call, get involved. It's a great, it's a great crowd of people. All right, that was, says here, the SISAL third workshop in Agadir in Morocco, where some of these analyses that I'm going to show you in a moment originated. I don't know. We can now do spot your favorite researcher. Anyway, so this is the records that are included in version 3. The brown ones are new in version 3, the green ones are in version 2, and black are records that have been identified, but for one reason or another they're not yet included. This can be standardization, this can be because not all the data is published, and so on and so forth. You can probably all imagine that there's lots of things that you can do at understanding regional or global climate with a collection of speleothem records from all over the place. But something it critically hinges on, and I think you heard about this in the talk about dating, is that chronology is key. So quite a few of the records in the early database didn't have an age model, or they were so old that the age model was no longer considered reliable. And so that's why we had to that's why we went back and looked at all the methods that had been used and selected those where we said, right, these are methods that are now being used to construct age models, and they span the range of what we expect the community to be using. And we implemented these in a way so that we could automatically run them with the information in the database. And what we obtained, I'll show you in a second how, was through the automated workflow for 500 of the 691 records. We got new age models that passed all quality control. This is one of the more challenging ones, and Tildy, where are you? I think this is one of the Momnu cave. This is Francis Morsix. Yes. So this is one of the Indian speleothem records. The key point is we included all of these, and yes, Copra has been translated to R, so you can just run it alongside with Salage, Beacon, Bacon, and I'll give you later the link on where you can find all the code to do this. Bear with me for a second. So this is how we described our quality control in the database version 2 paper. Every line is a speleothem record. And these are the different methods by which you can construct, let's go back, an age, so a depth-age relationship. In this case, depth, I can't even read how big this is, okay. Depth and age is going up to 16,000 years. So it's a declacial record, starting around 5,000 years before present. And you can see a couple of the challenges we face. I mean, many of you have built an age model, you have ages that don't fit. These are here in red because they were excluded. You have hiatuses sometimes that can be traced to something that is directly visible, sometimes it's not directly visible in the record. And all of this information is encoded in the database. So, including when a researcher thought this age is crap, discard it, then this is also marked. So the date is included and all the information is included, but yeah, so I think with very, very few exceptions, we always follow the recommendation of the original researcher. in construction of the age models. So yeah, when we then run the age models, the different methods succeed or do not succeed in running across hiatuses, with outliers, and so on and so forth. Different number of times. You can see that Oxcal has a hard time converging. I don't know if anyone here has experience with this. This is one of the Bayesian methods that posed a lot of problems. Whereas linear interpolation, yeah, well, it's just linear interpolation, so it works, right? We did a couple of checks, which meant, okay, there should be no reversals since we have a sedimenting archive. In this case, it was rejected directly. So if an age model did not find one realization where it was able to have a monotonous growth, then we rejected this method. The second one is that generally the age model should follow the growth rate changes. So if the ages are somewhere down here and the age model exists somewhere up here, believe me, I've seen it, then we were also like, right, this is not following the growth rate. And finally, this is the third one, which we wanted, was that uncertainties should be higher if we have no dates, or uncertainties should be higher around hiatuses. So this is an increase of the interquartile range of the age model. And as you can see, the green bar here shows us that we were able to construct at least one age model in 503 out of 533 cases. And as you can see, we built this on a quite heterogeneous database. It's kind of hard to see, but it's in the paper as well. There's lots and lots of types of different dates. You've seen that in the dating talk. And there's lots of ways on how people have built their records. But yes, D here, unknown, is almost 10%. So in 10% of the cases, we do not know how the age model was created. And I think in, well, the vast majority of the cases, we have no uncertainties of the age model. And that was the key reason. If we have no uncertainties on the age model, how are we going to evaluate whether changes in climate, or from the Little Ice Age to the medieval climate anomaly, or through abrupt events, are going to be synchronous if you have no means of telling the uncertainty of the age model, right? So that was a lot of interesting reading, also trying to figure out which one of these we pick, and this was a big conversation that we were having basically. And that is, I guess, also forming and informing. What we ended up with is a wide range of records with a wide range of age model types. Version 2, and you don't need to just look at the boxes. This is all the types of vectors that you have access to in the database. And all of these boxes are linked, because imagine each one of them is a text file with rows and columns, and you can jump from each of these to any other place in the database by following the linking IDs. So sample IDs, entity IDs, site IDs. So you can find all entities or all speleothems from one cave. You can find all samples from one speleothem in one cave, and so on and so forth. Get my drift. So you can jump around in all of these tables that contain all the information to construct H models, to analyze speleothem isotopes. You could even recalculate ages for quite a few of the records. All of these things you can do because it has been put in, well, by people like you or me. Basically people who sat there, sometimes with the original researcher, sometimes with the papers, and put in this information by hand. And this is a lot of work. It's not error-free, but there are quality control checks in Python and in R. And so this is a huge amount of information that's just there to be exploited. In version 3, we're going for an easier upload, which sort of worked. And importantly, because we expanded to maps, as I said, to scans, to trace elements, we needed to include new fields. So I think there's yet another color going to be appearing in version 3 and 1 or 2 or maybe 3 more of these boxes. But the concept is the same. It's basically linking all the information you have about this cave to interpret the record. It's linking it. And you can do similar analysis, similar workflows with different data sets or different Stevie-Thurn records. How we put it in, it's simple Excel workbooks. And you can download this workbook right now when you prepare your data set for publication and just provide it in this workbook format. And it will make your life easy because you know you have included everything that is necessary for the future for this record to go in version 4. And you have not forgotten crucial information. You could tell stories. Or you could grab a couple of those records, the black dots on the map, and do that and be a part of the next version of SISAL. It's very easy. One example of where age models matter and where it matters that we had all the information here, the original age model for this record, it's entity 342, Dennison et al. The black dots here are the ages, and the original age model is a smooth curve down here. And you can see that it sort of goes through the uncertainties of the ages at the bottom, but at the top, nothing in the paper told us that this species then was actively growing, and there's no date up here. So there was no real reason for this age model to not pass through the first date. And as you can see, all methods that we applied later were like, right, this is the first date, that I'm more or less sure about, I'll pick that one. You can see that the different methods, so linear interpolation, Bacon, Beekman, Oxcal, Copra, have different width of their uncertainties at different places in the record. And this is part of reasons for that are basically down to the assumptions made in the record, in the method. But that's fine. It's part of using multiple lines of evidence to assess, for example, when things happen. So this is just visualizing for these different age models what this would mean about shifts in the record. And sometimes it shifts these things by a couple of 100 years in this record that is only, I'm going to say, a couple of hundred years long. So it's substantial. It has an impact. So if you can run multiple age models, it's possible. I'm going to show you also the path to the code. SISAL science. So what kind of questions can we answer, or what kind of questions can we ask first? With synthesis, so having all of this data at our fingertips. Well, as you sort of saw from Matthias' talk on climate models, when we want to go from local to global climate dynamics, this is when really networks of data sets make a difference. And another part that Giselle also mentioned was that paleosynthesis, well, they're required to make policy-relevant statements. And I was really happy to see that this, as the first figure of the IPCC report, showing how another synthesis based on the pages 2K, temperature, so proxies for temperature that had been collected for the last 2,000 years, how this fed into the IPCC report and is now the basis for temperature assessment over time. And this is another pages working group, and I joined that as an early postdoc and basically doing analysis on the database and for the reconstructions as it was going along. So that was, I think, definitely a high point of my career. Of course, it shows us that what we're currently observing in terms of temperature change is unprecedented over the last 2,000 years, and puts it into perspective. And the right-hand side then shows the attribution by models to greenhouse gas forcing, essentially. So this is where it could go. But why is it so much harder when we work, or why is it, so, let's put it the other way around, why is it possible, straight and fairly straightforward, with proxies for temperature? Because it's temperature, and this is sort of absolute. We, however, are more focusing on hydroclimate, and this is also important, right? Hydroclimate modulates the risks for human societies. There's a big aspect of how we manage our water and the land surface and so on, but hydroclimate is certainly important, and present-day water risks cannot be neglected. We know it's super complicated, the processes that are involved, and that they do tie to the latitudinal energy budget, so how energy is integrated at the Earth's surface, in the atmosphere, in the ocean, and how energy is transported, because that is, in the end, how our climate engine works. Now, coming back to anyway, why is there more radiation out of the high latitudes? Because of transport. So, we are, okay, I guess I want to cancel that. The surface energy balance, so what we see in terms of temperature, sorry, geeking out for a short moment. So what we see in terms of temperature, if we look at the pages 2K, if what we think we see as temperature, if we use proxy records for temperature, is actually the sensible heat flow. So what you would measure if you put a thermometer there. That's what we think we have. But actually, the radiation that comes in is balanced by the latent and the sensible heat flux. And both impact the temperature, and they link to the hydrological cycle, so the energy transport over land and in the ocean. So yes, atmosphere and ocean collude in this, and when we discuss large global changes, so glacial, interglacial cycle, but even something as small as a little ice age versus a medieval climate anomaly, what we're really looking at is shifts in how energy is transported and how energy is manifesting itself as changes in precipitation and changes in temperature. In the end, what the system will always try to do is balance at the top of the atmosphere, right? And that is why hydroclimate is crucial to understand. It's totally missing in this perspective of warming in the past as well as in the future. And it's super hard, yet with spinethins we have a good chance of looking into this super hard problem. But it is hard. Because another reason why it's much more straightforward for temperature change is this is comparing the LGM to pre-industrial and a 4 times CO2 simulation. It could be the future. No, it could not be the future. This cannot be the future, sorry. But a 4 times CO2 simulation with pre-industrial, and what we see is that globally, so on the left-hand side, we have the absolute change in temperature. This is based on model simulations. What we see is that the sign for temperature globally under these large shifts is the same everywhere on the globe. Another reason why it's a lot easier for temperature to be, or temperature records, to be globally accumulated and giving a sensible picture that we can interpret, because the change manifests itself in a way that is globally correlated. There are patterns on top of this, so amplification over the continents and high latitudes and so on. So what we call polar and terrestrial amplification. On the other hand, temperature variability is also sort of linked to these changes in the mean climate, but in an anti-correlated fashion. A bit more complicated story for another day. But when we look at precipitation, again, another reason why it's much harder, why we have a hard time doing this and making getting there, that spiritual science, that hydroclimate changes can be globally integrated. It's because under these same temperature changes, we see actually decreases and increases of precipitation in different places, which links to the changes in circulation. So that is why we should not even see the same signal in different places. Add to that we know that the processes relating to hydroclimate can be hyperlocal. Think back a couple of slides when I had the diagram. We know that, right? So this is why our situation is a lot harder, and it's okay for you to struggle for us, to struggle to put this into a comprehensive, simple picture, because it's probably not going to be simple. So first order, what we see is that in a colder climate, we had less, so that's the purple, less precipitation in most places, except in what I call Mediterranean type climates. So in the mid-latitudes, so Western North America, Mediterranean, North Africa, South, that's mostly Chile, I think, South Africa, and so on. And that's reversed for warmer type climates. So depending on where your record is positioned in this, you should be seeing, from a thermodynamic perspective, different signals. So precipitation follows circulation, and Mediterranean type climates oppose global trends. On the other hand, precipitation variability follows, to first order, the mean pattern. So where we have increases of precipitation, we also have increases of precipitation variability. So having even information about qualitatively, as Spiriothem was growing in this time period, could already tell us not only that there was more precipitation, but potentially there was also more variability in precipitation. So this is a mechanism that is currently based on, well, climate model output, but it could even be providing information. So qualitative information could be providing more than just a statement about the mean change. And this is one of the reasons why we can say this is because there is a concept called hydrological sensitivity. So when we have, going back to the early papers of Allen et al. And Held and von Soden, 2006, which here is exemplified with global climate models. We have a global change in temperature at the bottom from the cold climates of the LGM to the warm climates that was the 4 times CO2 scenarios that I had here. And on the y-axis, we have the change in global mean precipitation. And they fall under this line. Most of them have something like a 1 to 3% increase of precipitation per temperature. So there is this property, and we would like to constrain this a little bit better. And one way how this could be done is by just having information on where and when we see increases in precipitation. So qualitative information on when and where we have more precipitation is crucial. An early way on how we did that with, that was not SISAL database version 2, but actually something like 1B or 2 minus, it doesn't matter, I think we called it version 1B. We wanted to look at how does glacial to interglacial climate change, and how does this change in our Spiriothem records. And for the LGM, we just had something like 9 records where we had a Holocene and an LGM oxygen isotope value. And that's just not enough. And so we really needed a need to increase this. We devised a way on how we can try to circumvent that. So if you want to look into this type of changes and you have the situation that you lack the baseline value for another climate period, essentially what we did is you assume that modern day ice escapes are your Holocene sample. And then you look at spatial transects. You can look at spatial transects along the pathways of assumed circulation patterns as well and look at how that changes in different climate models. But that was like the first, this is sort of like a protocol for how you could do model data comparison with speleothem records out of SISAL. And for glacial, interglacial, yeah, damn hard. Should be better now. I haven't checked how many more records we would have. And we can do so much more. I included this picture. This is from actually my PhD, and it's Southeast Asia. Just these couple of dots, these are proxy records, and I don't know for how long I spent time searching through Pangea, the NOAA database, individual papers, looking at the appendices, trying to get that all in the same format and have a code to access this in a way. Anyway, took a long time. In the end, what I can show here is that in the background, so this is, again, model simulations, and it's the color gives you the correlation between temperature and precipitation in this grid box. And you can see it's negative, and pretty negative, so the minus signs tell us that at least all -1 models agree that this correlation should be negative here, which means warm is associated with wet or dry? Sorry? Dry, yes. And the opposite. Whereas all our data sets say, well, when it was warmer, we have more precipitation. That's thermodynamics partly. I mean, there's a good solid reason. So, and later on, Ljungqvist et al., so that's a hydroclimate paper out of basically the Pages 2K network, did a similar analysis for Europe, and they also found this kind of pattern. And this is, I would say, still fairly unresolved. Why it happens, how we could resolve it, and there's, again, more layers of that I could go into that relate to what timescales models are built and what we're seeing when we're seeing a proxy record. But let's just say it would be a lot easier with speleothem records and delta 18O, and here we are a couple of years later doing similar types of analysis, now looking at isotopes thanks to SISAL. So in the background here, you have the correlation in models between here temperature and delta 18O, precipitation and delta 18O, and which of the two climate drivers is more strongly correlated to delta 18O on the right-hand side. And we see in the mid-latitude for most of the models, so this is from 5 isotope-enabled models, in the mid-latitudes, precipitation tends to win, but there's a lot of gray areas, which means it could be 2 to 3. Whereas if you look at the absolute signals, then the correlation to precipitation in the low to mid-latitudes is pretty negative. The correlation to temperature is pretty positive everywhere on the continent. So again, we have a tug of war with the isotope signal. When you look at the dots here, these dots have colors as well, and that means we've been looking at the delta 18O in the record and compared that directly, because it's last millennium, to the simulation. We make a couple of assumptions here, of course, but in principle, these two cover the same time periods. And we look at where is the correlation highest. And yeah, generally the correlations are weak. Typically, actually, temperature wins. But it's a fairly weak one. Right, so this is looking at 5 different climate models with water isotope-enabled tracers. So if your cave is somewhere one of these dots, then you can just go and download the data. It's all that we've parsed all the information from these 5 isotope-enabled simulations. You can just download it for any of the caves and do your own analysis with this. Another example, again, for the model is doing one thing, and speleothems are telling us another thing. Let's go back briefly. You see this phase pattern between the north of Europe and the south of Europe. And I only realized that when I put it together for SISAL. We see a similar thing actually. This is the SPDFM records, and the lines here represent correlations, and if they're blue, negative correlations between records. If they're red, positive correlations between the records. If there's no line, it means there was no significant correlation between the time series of those records. So, okay, that's the SPDFMs. On the other hand, we have the models, generally much weaker correlations, and they're all positive. That's in the supplement of our paper because we didn't understand it at the time, and I still don't understand it. But it was pretty striking when I saw that. And the question to me now is how much of that is temperature, how much of that is precipitation, how much of that is simply why are the models all correlated everywhere? Okay. But you start to see these patterns, and for a while you think maybe that just doesn't mean anything because the proxies correlate in all directions. And it also gives you a sense of humility for how much can an individual record do, how much can't it do. Anyway, but sometimes then later you come back and like, maybe there's something in here. We can do more. We can look at individual records. In this case, this is from Bunker Cave in Germany. We can take the model simulations at the grid box location, and as Matthias indicated, we can then, it's cool, it's nice that it's raining, I guess. We can model some of the processes. In this case, we model the path, or we take the precipitation weighted isotope signal from the model, a karst filter, and then we filter to the resolution, so basically the growth rate of the SPDFM in a couple of steps. This is, of course, let's go back. This is, of course, not all processes have no effect on SPDFM. But I can tell you, when you try to get this information out of papers, or from a researcher who was even there and is working there, that you would need to build a model to represent the processes that you think are important, you are going to spend a lot of time. And then you maybe end up with a model, like a karst model for one cave. And I told you now, SISAL version 3 has 900. And out of that, I think it's like 500 sites. All right, not gonna work, guys. So, karst filter it is. It's simple, it works. I'll show you in a second. What we see is, okay, precipitation is pretty intermittent. In other words, what we say is white. The distribution is white. This means the blue line here in the back. This means that there is no specific frequency at which we have more precipitation when we look at different timescales. So interannual, decadal, centennial, millennial. In the model, this is white. Our SPDFM records, that's the black line here. And this is not just Bunker Cave, but this is all entities for the last millennium. So our SPDFM records are not white. They do not have equal variability at each frequency or time scale. So from 2 years to 200 years, they actually show us that they do not vary a lot on short time scales. And yeah, still, that's what we know. That's because, of course, they're not rain gauges. And we have integration of signals and so on and so forth, or what we call a loss of or dampening of variance. And that we can mimic with the karst filter. So we can check how many years of effective filtering bring our records into alignment. And it turns out, is it in here? Yeah, so it's something between 3 and 10 to 11 years for most sites. There's a few sites which are very rapid. There's a few sites that are very slow, but for most of them, it's like in that order of magnitude. So that brings down our white precipitation signal that initially comes in. It's the blue one here. It's very, Gaussian distributed, and brings it down here with an increase of variance towards longer time scale. But what it does not do, and why should it? It does not bring us to more centennial scale variability. And reality and our speedothem records do show this. So one of the open questions, and I'm not phrasing it here as a very open question, is there anything in all our case sites that brings up our signal from on decadal, multi-decadal to centennial timescales? So is there anything changing our signal from what it should be and making it more variable on slow timescales? There's a couple of processes, and this is more like a thinking question, I guess, for when we're on a cave trip and if you come up with something that we know. So far, this has eluded us because it's a feature that we see time and again. Looking at proxy records for temperature, I spare you that part of the talk. And so right now we've accepted the working hypothesis that our models really do lack this variability. And sort of when you see, like if you also think back to some of the simulations Matthias showed, they're very stable. Yeah, but our records don't look like that. So we see this, and we see it here in the power spectrum. It just makes it very obvious. And the open question, if we accept that working hypothesis, is how can we improve our models? Can we get to precipitation change from isotope variability? You guys, let's get started. I don't know. Because, as I also showed, for quite a few of these records, they're from land, right? There's a strong temperature signal as well. So, this is where the trace elements perhaps also come in to partial out the different influencing factors, where new proxies, uranium, whatever, you take it, you're creative, come in, so that we can say with confidence our models contain the necessary processes to simulate precipitation change, because that has an impact on our daily lives. Although we don't have to cycle today, it's raining now, but we're fine, right? We just get wet on the way to the bus. Today, that's not very critical for us, but whether it rains or not for our society is very critical. And here we have a way forward with our speedothem records. And just in case you thought, okay, this is just one model, HATCM3, and tends to be my simulations. No, this is the follow-up paper from last year, where we looked at these 5 models, and they all show it at different degrees, but they all show this lower variability on centennial timescales. So I think it's easy to say that they do that. We've also been able to look at the ratio of O18 to C13, how it changes with timescale. I think there we could definitely profit from a better regional perspective, and in particular people identifying with regions looking at this, not us. But this is at your fingertips if you're interested in this. And possible because we have all these records in the database. So, there are many other publications. I've shown you now, I think, only 3 that I happen to be involved in, sorry. There's tons of other publications. They're on there. Check them out. It's very straightforward also to get involved in them, because you can join SISAL. The first step is to join the mailing list. Another way is to just go to the new SISAL web app if you first want to play a little bit and want to check this out, where you can just see what's in there. What's in it for me? Is there something that could relate to my record? So you need to enter your email just to prevent spamming. You can then have a latitude-longitude filter, or you can search for a specific site. You might need to try a couple of different spellings. You can also filter by age if you say, oh, I look for something from the last interglacial, and so on. Speedothem types, and so on. You can filter, and there's also an advanced panel where you can query any of the fields that you've seen. Okay, and this is when I did, okay, just give me something that we have roughly in the area. So we already have in version 2 now South America solidly represented, but of course there could be more dots, and you can click on the dot, and you get all the data and all the information. And there would be advanced query parameters again. Another way, and sorry, this is a lot more busy, is to analyze the database in R or in Python. I know you had a time series analysis workshop. There's code. It's usually linked with the database. You can just download a zip file. It's either a zip file or a MySQL. This is the link. Make sure you know where you put it on your computer. It's usually the first challenge. You can then look into the database files. As I said, each one of these boxes on the database plot is a CSV. It's just a table. You can look at it, or you just open, this is a markdown file that I prepared, or Janika and I prepared for you. Actually, we prepared it for KR9. I don't know, some people were there. All you need to do is change the path at the top to, of course, reflect where you stored the database, not I stored it. And you can play with it and create some of these graphs that we've seen today. It's really straightforward. There's more code. All of this is online. This is part of SISAL to create this. If you want to do the multi-model comparisons, the code is on GitHub, on our GitHub. There's also the climate variables and the simulated oxygen isotope ratios. The age model ensembles, if anyone wants to, I don't know, see if one is better for any other site, we've provided them all, so the ensembles, the raw data. This is particularly interesting if you want to test, for example, if a specific event for your site where you're now maybe creating the first age model ever, if it really aligns with the other ones. Then you don't use what's in the database, which is the confidence intervals, and a median age model for each site and method, but you can go to the original raw ensemble data and test with 1,000 realizations, or 7,000 if you include all methods, if your conclusions are robust. So that's also in Zenodo. And there's some other time series analysis stuff. Right, so getting there. SISAL needs your record. Find the workbooks. The best way to get it is probably to email sisaldatabase@gmail to really get the latest one. There's also a monitoring workbook where I was specifically asked by Nikita to plug that we need more oxygen isotope monitoring data, and we do need more people asking questions. This doesn't need to be a big amount of your time. Something that it provides for you is archiving what you produce in your PhD, in your postdoc work, and preserving it in a way that is findable, accessible, interoperable, and readable. And this is really important so that we can make a difference in the future as a field and as paleoclimate scientists. So, SISAL is cool. It's a community effort. It's there for you. You join. It's documenting the achievements of the StudioFem community. We're just scratching, we're just putting finishing touches on version 3 of the database, and now is the time to join with your science questions. Because you can be one of the first ones to play with this data and impact the conversations we're having. Impact also phase 3 with the questions. It can benefit your PhD project. So something I really recommend is to not be like, okay, she talked about SISAL, this is great, I'm abandoning my cave, I'm just going to spend time with the computer now and churning out papers. Not what I recommend. But maybe taking a couple of hours here and there and maintain a solid side project, maintain those conversations, because that can make a difference in the long run. That might be the paper that gets published, or your own gets stuck, or that one gets stuck. Anyway, no, usually they don't, right? It can make a difference, and it puts you into the conversation. This is true also for other pages working groups, so mean, I'm supposed to highlight SISAL in particular, but there's lots of other pages working groups, and most of them have regular conversations. They're open and they're fair. So if you contribute to a product, you will be acknowledged for that, and there's clear rules for this. Yeah, and I'll end with a similar note than Giselle. Synthesis, I think, are crucial to evaluate local to global climate. And there's no reason why we shouldn't do this. Don't leave this to non-experts, because I know quite a few modelers who go out there and you're like, all right, there's all this data at my fingertips. Let me play with this. And they ignore evaporation. They ignore, kinetic fractionation. Why? They don't know about it. So these people sometimes are smart enough to join efforts like SISAL. You can guide what they do, or the other way around, they can provide you with information as well. So don't leave this to non-experts, the global climate stuff. You can join on this. So again, this is a community effort, in particular Franzi, Nikita, Laya, Janika, but also Carla, who was an early master student in my group, contributed to this. SISAL is cool. It's funded. The network activities are funded through Pages, which itself is funded mostly through the Chinese Academy of Sciences and the Swiss Science Foundation at the moment, but this changes as well. Join, and thank you. Let's go to the field trip and think about stereothams.
Thank you so much, Kira, for that talk. We have time for some questions.
Burning questions. If not, I'm very happy for these questions to be spread out. But if you have questions, go ahead.
Yeah.
We don't have a guidance video or the guidance figure to show how to use your SISAL database.
There are videos explaining, yes, so the question was if there is videos or figures on how to use the database. Yes, so the description papers, so for version 1, version 2 in ESSD, and also version 3, which is just about to be, it's prepared for submission for ESSD, they already include some of this information, so how to access the database. But how to use it, there's no limit to how you could potentially use it, right? Because that depends on the science, on the research question. How to access it, this is something that we have prepared. It doesn't change from version 1 to version 2 to version 3. So that, I think, is also on the Pages YouTube channel.
Yes, I know, because when I use the database version 2, I found that maybe it's difficult for me to use the Python or R So maybe I need the guidance video to show how to use it step by step.
Yes, so it depends on your research question. If you say, okay, I'm particularly interested in this region, then you can go to the web app. So this is for the beginning. Or maybe also this is all you need, right? You can go to the web app and then find exactly those records that you want and analyze them in whichever environment you feel comfortable in. However, I recommend, so once you've downloaded the data set, and that is essentially the recipe here, it depends on how big your question is, how much model data you want to put in. If you want to go from plotting them together to quantifying, okay, here they change in time. This is the way age uncertainty does not affect my conclusion. If you want to do this, then you need to take a programming course or become very friendly with the help function or have good friends. It is not, yes, we all have different learning curves, and this is okay. Or join a conversation in a Pages working group where there might be 1 or 2 people who find it very easy and some who find it harder. So give your question to someone sitting not virtually next to you. Yeah, so there's different ways. I think it's not possible to teach. Some of the analysis are in there, in this script. And all you need to do is run it and it produces it, and you can change a couple of the figures. But yeah, I would say that the science questions can be really broad. And I can just say, you know, it's a good practice to, when you run code, when you write code, to share your code, when you share your papers, so then others can learn from it. And you can go to any of our papers and download the code to do the analysis. What we cannot do is hand-holding, right? So that's then the part of joining a conversation amongst people in the Pages working group, finding like-minded people with similar questions and joining with them. We have videos, but I think this recipe is the way to get started.
Any other questions? Yeah.
I want to ask about your SISAL and climate model. So can they reproduce a past climate extreme event, a different past climate extreme event like Prof, rain that recorded by special team? So can they reproduce and like how accurately they can help us simulate the intensity or the density of these events?
Okay, let me see if I get the direction of your question right. So you're asking how accurate can climate models and SPELIOTHEM data represent changes in extreme events?
Yes.
That's a very complex question. And if you ask me, if you phrase it in a different way, can models accurately reflect reality, then by definition my answer will have to be no, right? We've seen this in the afternoon. Models are a representation of reality and the processes we understand. And I think the complexity of the answer can get very deep. With regards to, I would throw this question into the room and say, what multi-proxy measurements, observations from your cave can tell us about extreme events? That's step one. There could be flood marks, the absence of information, there can be layers in your SPELIOTHEM, there can be a lot of things, right? And the next question then, because I'm talking about SISAL, is this information in SISAL? Probably not. On the other level, I did say that in our, let me go back. We do see a connection, we have a tendency to see changes in extremes also where we see changes in mean precipitation. So there could be mechanistic reasons why one should tell us about the other. But this is speculating, because right now I would say, a priori I would not trust the models, and I would also not know what to look for in the individual records. It's a complicated question, but you're really right in bringing it up, because the reason why I've been telling you all these things about hydroclimate is because hydroclimate is sort of a direction Pages is going, Pages 2K, but also SISAL is thinking in this direction. And so with questions like these, you're joining a good conversation there. But I can't definitively answer this.
Thank you.
Yeah.
One last question?
Or not? We can.
Okay, thank you again.
Yeah, thank you.
Okay, then I think we have some announcements. Right?
Leave it there.
Yeah, maybe we'll take a 5-minute break
Yeah,
and
okay.
reconvene.